Hi again. This week we're going to tackle a concept that will be with us for a good part of this semester actually, certainly in mechanics and flow, in the cardiovascular system, in the major project. And I'll spend a little time on the concept and then get into a little bit of the equations we use to deal with it. And then soon we'll get into complex computations using this whole concept of a feature of flow that we really haven't talked about directly, and that feature is compliance. So let's spend a little time thinking about compliance, but first we need to give it a little bit of context, and that's of course our vascular system. This is where blood flows. That's our main area of interest, and so we want to understand how compliance plays a role in the blood flow. We've spent some time thinking about resistance, Passeur's law, and the flow of blood as a function of pressure, as a function of resistance, radius, all these sort of terms. And now we're going to add another feature, another facet to the way that the blood flows in the vessels. And it's really meant to capture an important aspect of vessels, their mechanics, and that is their ability to stretch, to distend, both under pressure from, let's say, the blood pressure, or external pressure that we might apply through a blood pressure cuff, but also even through the regulatory control of our nervous system. So compliance and the shape and size and cross-section of the vessel are an important factor of resistance, but they're also captured in the concept of compliance. So where does compliance come from? It's really a function of the vessel wall structure. So the compliance is the purely elastic distending of the vessel wall under pressure. So it's not the contraction through muscles, it's not the nervous control, those all play a role in blood flow, but this is the passive expansion of the vessel walls due to pressure, and then their elastic recoil if that pressure changes. And if we look across that system of vessels you just saw and compare different features like the cross-sectional area, the wall thickness, even the structure of the different tissues that make up the vessel walls in different parts of the vascular system, then we see there's quite a variation. So the endothelium, the basic innermost layer, that exists in all the vessel walls. And as we move from aorta to artery to vein to the vena cava, that's the main larger vessels, relatively larger vessels, we see a different balance between the elastic tissue, the smooth muscle tissue, and the fibrous tissue. And the fibrous tissue will make things stiff. The elastic tissue will make them elastic, of course, as you understand. If we go into the very small vessels, which is where, of course, all the transfer occurs, all the movement of particles, ions, gases across the membranes from the inside or outside of the cell, or the inside or outside of the vessel, back and forth. Then we see that the structures get even simpler. In fact, once we get down to the capillaries, the only thing left in the vessel wall is this endothelial layer. Nothing else is there. It's just a little tiny tube made up of endothelial cells. And that's where, again, the transfer happens. That's where there's the least amount of tissue in the vessel wall to get in its way. So all these things determine the function that we also see of the various vessels. And most of them have the role of distributing the blood. They're the shipping department. They're the trucks. The infrastructure. The trucks are actually more like the red blood cells if we're thinking about oxygen. And the vessels themselves are like the highway system that carries them around. And the only real transfer, the only real movement from the truck to the shop or from the truck to your backyard, those transfers happen only at the capillaries. So there's different functions in different parts of the vasculature. So that's the system we're working within. And now we want to talk about the role compliance plays in that distribution of the blood flow. So this is now the context of blood flow. Now, we've talked about compliance in general in the textbook. You've read that section, and you'll know that certain structure, shapes, everything really in our body has some elasticity. And if we picture that elasticity, which could be compression in a bone, let's say, but if you picture a closed container, so picture a balloon or an enclosed, or your bladder or some other structure in our body that's closed, then we will see that as we apply pressure to that container, the volume will increase. And that ratio of the increase in the volume as a function of the pressure we apply, that's compliance. So compliance is sort of like the elasticity, although it's a somewhat different concept. Elasticity has to do with more the recoil, how it comes back. But the compliance is just the extent to which volume changes in the face of a change in pressure. And so when we talk in these terms of volume changing as a function of pressure, then we naturally draw those things in a graph on the y and x-axis. We have volume on the y-axis and pressure on the x-axis. And we can plot, we can make measurements, eventually we'll see equations that describe this, but we'll get a function, we'll get a curve. And for some regions of pressure, that curve is linear, straight line. You've been learning all about this. You'll notice in this example that the curve is also a little different from what we've seen before in that it has an offset. It doesn't cross through 0, 0. So the idea here is that the volume, even when there's no pressure, doesn't go to 0. That's called the residual volume. You've learned about that too. That's an important element in the calculations we do, and conceptually also important to realize that the vessels don't naturally or automatically close down when there's no pressure inside them. They maintain some volume that we call residual volume. Again, here you see it in the example of a closed organ. And now we're going to apply that same concept to vessels, which are a little different. They're open, there's flow allowed through them. And because they're vessels that allow flow, we also have to think about them in terms of their resistance. And we've seen graphs like this. Here's a simplified version of flow, the resistive flow, the flow described by Poiseuille's law. And you see blood flow on the y-axis, and you see arterial pressure. In this case, could be any blood pressure. This is for an artery. Here you see the relationship between the two. And as we've described before, it's fundamentally a linear relationship, at least some of the time. And in this simple case, we've assumed it's linear, which means that it has a slope. And the slope we can see is delta Q over delta P. And we know from our Poiseuille's law, which is summarized there, that the slope of that line is 1 over r. So that's nothing new. What's new is this next part. So the new part is compliance. And there we plot volume versus pressure, just like we showed you before. And we see here that the lines are not terribly linear, at least not over the entire extent of the pressures. And we see the pressures are in the x-axis are pretty reasonable physiological pressures, going from 0 to 200 millimeters of mercury. So that's a not ridiculous range of pressures. We know that normal systolic pressure is 120, but when a patient has hypertension, high blood pressure, those pressures can easily get above 200 millimeters of mercury. So this is a very physiological range. You also notice that for the first time, we're going to distinguish between arteries and veins. We didn't before when it came to blood flow and resistance. It was just a function of cross-sectional area, the length of the vessel, the viscosity of the blood. That's really what determined the resistance to flow. And that was independent of the vessel wall structure. Compliance is different. In compliance, the vessel wall is everything. It's the whole story. It determines how much stretch there is in that vessel when we apply a certain amount of pressure. And as you see here, the curve for artery is lower. So that means that you have less volume change for the same amount of pressure than the venous compliance curve. The venous compliance sits overall higher. It has a different shape. The venous compliance is probably a little bit linear in the beginning and rapidly becomes quite nonlinear, whereas the arterial pressure starts linear, bends a little bit, and stays fairly linear. So there's very different characteristics, as you would expect, between generic arteries and generic veins. And again, there's variability depending on where the artery is in the system and where the vein is in the system. So these curves describe something that is also a ratio, and the ratio here is blood volume on the y-axis and pressure on the x-axis, and that ratio, delta V over delta P, is the definition of compliance, which you also see there. So we can think about the flow of blood being a product of these two different scenarios, and you can see how they're related, because if you imagine pressure increasing, then volume will increase, and if volume increases, that means the vessel gets bigger, It only gets bigger because it distends outwards. And if it distends, then its radius changes. And if its radius changes, then its resistance changes and its flow changes. So these are all tied together. And our job is going to be over the next couple of weeks to figure out how to sort all that out and predict how blood will flow in a vessel that is not a rigid tube, but is compliant. And so we're going to take snapshots, in a sense, and say at this point in time, there's a certain amount of compliance in the vessel, there's a certain amount of pressure, that gives a certain amount of volume, and from that we can even determine what the flow rates are going to be. And we'll see how to represent that schematically, mathematically in future lessons. Today I want to focus on the concepts. And the next concept is to, again, try and differentiate between what happens when blood flows through a bunch of tubes that are rigid, that have only resistance, so they don't distend. The resistance, the radius is the same, the resistance is the same, compared to a vessel that has some distensibility, has some compliance. And here's a schematic that shows very approximately a schematic for a pump. That's on the left-hand side. And you can see there's an inflow into that pump and an outflow out of that pump. And what would we expect that relationship to be between the inflow and the outflow? This is a little bit like what the heart does, as a matter of fact. It pumps, it takes blood in, and it pushes blood out. Overall, we would expect those flows to be the same. So whatever goes in also comes out. That's also a feature of the heart. Again, integrated over some period of time, seconds maybe, or minutes. And so overall, we have a net inflow and outflow being the same, which is as it should be. But what we see changing is the pressure. So the pressure going into a pump is going to be lower typically than the pressure that comes out of that pump. That is the purpose of a pump, is to increase pressure. So here we have a scenario where we have a pump taking blood from the input side, adding pressure to it through mechanical energy, and then pushing that blood through those system of vessels which are purely resistive. If they're purely resistive, then we can understand how to treat them. We can apply Poiseuille's law to each one of those. We can figure out the resistance of each one of those. We have resistances that are in series, and we have resistances in parallel. There's a structure here that you can actually figure out quite easily mathematically, and you can analyze that circuit. In fact, you can replace it with a schematic circuit that looks something like this, where the pump has become that triangle, and the little blocks are just the resistances that we'd see along the way. And whatever network of resistances we would have, there would be sequences of series resistance, parallel resistance. We can collapse those to make a figure like this. And so we end up with different resistances that arise in the blood flow. And to each one of those, we can determine what the pressure change will be. Because the flow, we know, is Q in or Q out. They're the same value. We have the flow. We know the resistance because we know the structure of these vessels. And from that, we can figure out the pressure change that vessel, that segment of vessel, brings about. And we can completely characterize this system, and we can even draw a curve like this that shows how the pressure drops. And the pressure will drop more through a high resistance vessel than through a low resistance vessel. That's why the steps can be slightly different sized. But at the end, the pressure at the right side, that P3, is going to be equal to the pressure we have on the input again. That's the P in. And that's the schematic and explanation of a purely resistive flow. Now, a key point here to keep in mind is that time is not a factor. What do I mean by that? What I mean is that if we were to change the pressure in that system, in that pump, increase that pressure a little bit, then instantaneously the pressures would change throughout the system. It's a rigid system. All the conditions I just described change instantly. There's no time in any of those calculations. T doesn't appear in any of those equations. And so we know that time is not a factor. Every time instant is like any other time instant and is described by the characteristics of the pressures and the resistances and the flows during that time instant. So how is it different for compliant vessels? Here we have a sequence of events, and already from that you can tell there's going to be time involved in this whole process, and that's an important part of it. So here's a situation where we see flow in a vessel that's compliant. You can't really tell it's compliant. It looks pretty straight at this point. But trust me, it has some compliance. Maybe this is at its residual volume. And so we have Q1 going in and Q2 going out. And of course they are the same, exactly. We have a radius, we have a length. We could figure out the resistance of that vessel. We could characterize that vessel using Poiseuille's law, figure out the relationships, the pressures and the flows and resistances and all that fun stuff. However, now we're going to do an experiment. First, a thought experiment. We're going to have Q1 suddenly jump, suddenly become larger. So we're going to say Q1 is now larger than Q2. Q1 is larger than Q2. What does that mean? It means the blood flow rate going into that segment of vessel is larger than the blood flow rate leaving that vessel. How can that happen? If this were a purely resistive vessel with a rigid tube, not compliant tube, then the millisecond that Q1 went up, Q2 would go up with it. They would go up perfectly in synchrony. Here, though, we have a compliant vessel. And so the vessel, because of this change in flow in and flow out, will gain more volume. Volume is conserved. Conservation laws, you've learned them in physics. They apply to the body just like they do in other situations. So we have conservation of volume. So the flow going in and the difference, more important, between the ingoing flow and the outgoing flow, that determines how much volume change there is. It's a product, as we'll see, of the differences in those two flow rates and the time during which those flow rates are different. So we just multiply. We multiply the difference by an increment of time and say that's the amount of volume that's gone in. And the longer the time goes, if we know the Q1 and Q2 in each case, we can just keep adding to that incremental change in volume, that increase in volume. And then the shape schematically gets bigger. This is what I was describing of a compliant vessel. That increase in flow leads to an increase in volume, and that in turn leads to an increase in pressure. And the relationship between the pressure and the volume, that's what compliance describes. So if the compliance is high, the vessel will get quite a bit bigger. And if the compliance is low, the vessel will only get a little bit bigger. But if it's compliant and there is a difference in flow, there'll be at least some difference in the flow leading to a change in the volume, leading to a change in the pressure. And that's the scenario that we have to describe. How does that change the overall flow rate? It's going to change as a function of time. And how is it going to eventually settle out? Well, we'll see in a second that eventually the Q2 will again equal the Q1 as long as Q1 stays constant. Eventually Q2 will equal Q1. We'll have a steady state again. That's necessary to have conservation of flow, conservation of volume. And so how does it get there? What are the steps? How do we figure that all out? That's what we have to think through. So far, just think about, and again, it's sort of a thought experiment. So again, we have Q1 larger than Q2. That's the first event we have. And then what happens? We get an increase in volume because we have differences in flow rate and we have some time that goes by, so we're at T1. At T2, that pressure increases as a result of that change in volume as a function of the compliance of the vessel. We can calculate that quite literally. And then, of course, Q2 eventually increases. Takes a little bit of time, but if Q1 increases, initially, most of that new blood will just go into opening up the vessel. But eventually the vessel will reach the end of its increase in volume because the pressure difference has also reached its maximum. And at that point then, Q2 will start to go up. So Q1 has gone up, Q2 is going to go up and follow it with some delay. A delay, again, is a function of the compliance of the vessel and the pressures. But eventually Q2 will equal Q1, and both those numbers will be larger than the original flow. Let's call it Q0 that we had here before anything changed. And that's the sequence of events that occurs when we increase the flow into a vessel. And we're going to capture that mathematically. We're going to figure that out. It's not so hard, but it's harder than Poisson's law because there's time in it. It has these derivatives and all that stuff you know from calculus. One question that I'll address with that, if you look at that scenario, what do you think about the cross-sectional area or the radius? Do you think the radius is any different in the second case from the first case? And then what is the consequence of any change you have in that radius? And then if you have the radius, if the vessel's ballooned out like that, wider in the middle than it is at the edges, how are we going to accommodate that? Because it's not the whole radius that's increased. It looks here like the radius at the middle is increased. So we have radius at different segments, different radius values. And we have to figure out a way to calculate those sorts of very realistic scenarios. And we have ways of doing that too. Like I say, we'll get to that. Now, another way to think of this whole problem is through an analogy I came up with, thinking about this a couple of years ago. I said, what if we have a container like this? So the black line on the outside is the container. We have something, water flowing in, Q1, and at the moment, Q2 is 0 because the level at the right-hand side is not high enough. So as Q flows in, it's larger than Q2. It'll keep flowing in, and the volume will go up. And of course, with that volume will go up the hydrostatic pressure, which is a function of the height of the water. So the water column P1 is really the column between the difference in pressure between Q1 and the bottom. And then as that volume starts to go up, we get an increase in P2 as well. So we have an inflow pressure, an outflow pressure, and an inflow volume or flow rate, a flux, and an outflow. And then eventually, as that gets larger and larger, it starts to flow out through the right-hand side. And at that point, we have Q1 going in, Q2 going out. And if the conditions are more or less right, then the pressures will balance and the flows will balance. And as much comes in through Q1 will flow out through Q2. Again, as long as the resistances of those two vessel segments are, accommodating and they can handle the flow rates with the pressures involved on them. But what happens now if we elevate Q1? We artificially increase Q1, the flow rate going in. What's going to happen? It's like compliance in the sense that that's going to raise the level of water inside the chamber. It's going to raise the pressure, that P1, and cause more increase in flow eventually for Q2. But initially, that flow difference between Q1 and Q2 is just going to increase the volume of water in that chamber, just like it did in the distensible vessel. And that increase in volume will increase the pressure, the hydrostatic pressure. And you see the little arrow in the middle. So it's an increase in the volume that comes about, and that will increase the outflow. So we'll have a new condition. We have Q1 primed going in and Q2 primed going out. And that's what really describes the flow. And then eventually we'll get a new equilibrium, assuming there's enough space in there and the resistances and everything balances out. You can sort of picture how you could tweak this so that nothing more happened except, Q3 got to a certain level, the chamber filled up, and Q3 going out, the other side was at a certain flow rate, and everything was sort of stable again. We had kind of a steady condition. And so we can think about compliant vessels as doing the same thing. Instead of the level rising up inside that chamber, we get the volume increasing because the vessel literally gets bigger. We have more volume inside that vessel. And so for a while, we have flow going into and staying in that chamber, that segment of vessel. And so we have flow going in, flow going out, and the difference between the two is a flow rate that increases the volume, in this case of the chamber, in a vessel, increasing the volume of the vessel. And that's really how we can think about these things. So to summarize, what are the main points here? Flow in vessels, in real compliant vessels, involves both resistance and compliance. And we have to keep track of both. We have to be able to think about both. The resistance is instantaneous. Any change in incoming pressure or flow will instantly change the scenario throughout the whole circuit, if you will, if it's purely resistive. But compliance takes time. Remember, we got an increase in flow, then there was an increase in volume, then there was an increase in pressure, and then there was an increase in outflow. And that takes time. And that time dependence is something that we'll talk about again and again. And we'll get into the details of that. Compliance, as you saw in those diagrams, is rarely linear for very much with respect to pressure. So the increase in volume with respect to pressure is not a straight line. It's maybe piecewise a straight line, but it's not as linear in practice as we saw with, for example, those resistances or 1/over resistances that we got when we compared flow rate to pressure. We looked at that Poiseuille's law relationship. So we're going to have to get our heads around that. The compliance is going to be nonlinear. It's going to depend on the pressure that arises. And you can kind of see how this is all getting a little complicated, but we'll sort it all out. And the other fact that you saw from that approach is that arteries and veins have very different compliance values. So unlike the resistance, which never even discussed what the vessel was made of, what kind of vessel it was, compliance changes with the type of vessels we have. And those are key differences that we'll again kind of process, but the point of this thing is to really think it through in a qualitative sort of thought experiment type way to start to picture what might be going on.